you'll notice the light doesn't travel in a straight line. Instead, it bends along the water's flow. At this point, the fluorescent-like water stream emits a strange red glow. So the question arises, we learned it in middle school physics that light travels straight in the same medium. How does it bend? If we zoom in with a lens, we can see that when light passes through a small opening, it doesn't bend directly. Instead, it keeps refracting. This phenomenon is called total internal reflection. So what is total internal reflection? We can learn through an experiment. Aim a laser at a semicircular glass. When the angle of incidence is 0, the light does not bend. As the angle changes, the refracted light bends more. This is because air is less dense than glass. Thus, the angle of refraction must be greater than the angle of incidence. When the angle of refraction reaches 90 degrees, -1 internal reflection occurs. It has many applications. One of the most notable is in optical fibers. The inside of the fiber is a medium of high density, while the outer layer is less dense. When light enters, it undergoes total internal reflection at the interface. Since there's no loss of light, signals can be transmitted over long distances. Moreover, mirages also occur due to this principle. With higher surface temperatures, air temperature rises too. When light travels through cooler air above, it moves from a denser medium to a less dense one. As the angle increases, once it reaches 90 degrees, total internal reflection occurs. The reflected light then enters our eyes, creating a mirage. Water droplets continuously fell under the light. A three-dimensional water figure started running. This raised a question: do the droplets actually stay in the air? The secret lies in the clever use of controlled lighting. After filming this magical scene appears. Is there such a thing as water droplet control in real life? The answer is yes. In 2018, a design team from California invented an interesting desktop gadget. When water droplets fall on the device, they appear to be controlled, floating freely in the air. After adding more droplets, they align neatly. The principle used here involves sound waves. Above the device, there's a transmitter that emits sound waves. When the sound waves reach the reflector below, they bounce back. The reflected sound waves overlap with the incoming sound waves. Since both sets of sound waves are emitted from the same source, but travel in opposite directions, a stable standing wave is created. From the side view, there's a continuous point called a node. Conversely, the point with the highest amplitude is called an antinode. Theoretically, if an object is very lightweight, the upward pressure in the levitation device only acts in two directions. Once the upward pressure reaches equilibrium with the weight of we pour a cup of clear solution onto a piece of tissue paper. At the moment of contact, the tissue starts to turn black, being corroded. This is the power of concentrated sulfuric acid. Switching to a steel wool test, as the liquid is poured, the steel wool immediately produces a large amount of brown smoke. Gradually, the steel wool changes color. This demonstrates the power of nitric acid. If the previous to acid shocked you, then the next colorless or slightly yellow liquid will astonish you even more. It requires special containers for storage. When the container is opened, white smoke is released. When it's dripped on sugar, the initial effect may not be as intense as the previous acids. But once water is sprayed on, a magical phenomenon occurs. The sugar immediately starts to darken, carbonizing. Next, and we repeat the test. The reaction is even more intense. This is the second strongest acid, chlorosulfonic acid. It reacts violently sulfuric acid and hydrochloric acid, releasing dangerous acidic vapors. Inhaling even a small amount of this smoke can harm the body. So, what is the known strongest acid? It is fluorosulfuric acid. This liquid is 2 million times stronger than pure sulfuric acid. When fluorosulfuric acid is dripped on chicken skin, the skin rapidly contracts, leaving deep holes. Finally, pouring it directly reveals the meat being rapidly corroded. The texture resembles that of cooked meat due to its extreme acidity. It can even explode upon contact with water. Imagine the horrific consequences if it were to touch human skin. Even the softest water can exert tremendous power. Did you know this? It's called a water jet. which can cut through steel. If I had to describe it in one word, I would say it's like a knife hidden in water. What appears to be soft water can exert shockwaves powerful enough to break through turtle shells or even tough bulletproof glass. Such powerful force, how can soft water achieve this? In fact, water alone isn't the only component. A material called garnet is using an ultra-high pressure pump. The mixture is pressurized to between 10 to 400 megapascals or even higher before passing through a tiny nozzle of about 0.1 to 0.1 per millimeters. When the water jet is released, it can reach speeds of nearly a kilometer per second. This is roughly 3 times the speed of sound. When this high-speed water jet encounters materials, it acts like a cutting tool made of steel. It effortlessly cuts shapes with a smooth surface finish. So what happens when it encounters darkness? You can see that when the switch is activated, the sharp jet pierces through a black key as easily as cutting tofu. As the pieces are cut away, the black key even is reduced to thick aluminum block. Meets the same fate when submerged in water at high speed. I must say, the power of this water jet is astonishing. So friends in front of the screen, who do you think can compete with a water jet?